right, hey y'all, it's Mr. Kyle Myers Mathematics, and let's just jump into it. If you're wondering why I have a decorated American flag, the short answer is because this is the last video that I'm doing in the series, and it's it'll be coming out on June the 30th. I'm not going to do another part of the series in July. But July 4th is, American Independence Day. So that's the short answer. If you want the longer answer as to why I decorated it the way I did, you can stick around and catch that at the end if you care to know. But let's go ahead and jump in. A bank account earns 5% interest compounded monthly. Suppose that $1,000 is initially deposited into the account, but that $10 is withdrawn each month. Show that the amount in the account after n months is a sub n equals 1 plus 0.05 over 12 times a sub n minus 1 minus 10, and a sub 0 is 1,000. Okay, well, let's actually start with a sub 0 equals 1,000. So we know that because n is the amount of time that's passed in months. So when n is equal to 0, no time has passed, aka the initial amount, which they said was 1,000. So that's why a sub 0 is 1,000. As to the rest of the recursive formula, it is recursive, right? So it's just saying, like, what do we do to get to the next step? And so it's going step by step. And the part that's in here is actually just the compounded interest formula, which I'll write off to the side here. I didn't give myself a lot of space because I have a giant flag on here, but I'm not even sorry about it. So A is equal to P, and then that's 1 plus R over N to the nt power, right? So compounded interest formula is this. And I'm not going to write out what all these letters mean. I'm just going to say it, but this is back from, I don't know, like pre-calc algebra 2, something like that. A for answer equals the principal. A would also be the ending amount. So you could say A for amount, specifically the ending amount, is equal to principal, the initial amount, times the quantity 1 plus R is the rate as a decimal, divided by N, which is the number of times compounded in a year, all raised to the nt power, where n is the same n, number of times compounded in a year, times t, which is measured in years. Okay, so if we alter this for our purposes here, we would say, well, for one, the initial amount is 1,000, but if we're going to leave that more vague, then p would just be a sub n minus 1. For n equals 1, that would be a sub 0, which would be 1,000. And then that would tell us what a sub 1 is if I plug in 1 for n here. And this is a different n than over here, by the way. So I'm not doing this super properly, but you get the gist of it. So 1 plus r, the rate, is 0.05 as a decimal, right? So 0.05 divided by n, the number of times that it's compounded in a year. Well, it's compounded monthly, and there's 12 months in a year, so it's compounded 12 times in 1 year. This is the part where it gets tricky, because I would actually put a 12 right here. However, we're looking at what's happening month by month. And so that would mean that t, which is time measured in years, would be 1/12. 1/12 of a year is 1 month. So t is 1/12 because I'm taking this one step at a time. The compounded interest formula is an explicit formula. It gives me whatever future amount I want, but I'm using it as a recursive. I'm trying to use this explicit formula recursively. So that's why I kind of have to tweak it. I'm going one step at a time, 1 month at a time, which is 1/12 of a time. Then at the back end of that, I'm going to take $10. When I'm done doing all of that, I take $10 off. So that's where the minus 10 comes in. And if you clean this up, you basically just get what we've got. So this is essentially the reasoning. You can add some of the words that I said as well if you want, but this is basically going to simplify they have. And I'm going to write it exactly how they wrote it. That way we're ending with exactly what they have. Other than they put a slash like diagonally there, but semantics. So we wrote out what they have, and that's how we got that answer. So that should be enough evidence to show that we're done with part A. Okay, part B. How much money will be in the account after 1 year? Well, this is going month by month, right? So we would plug it in and figure out what it is in the first month, and the second month, and the third month, and so on and so on. You could find out what the explicit formula is. Sometimes the explicit formula is not too difficult to derive from the recursive formula. So for instance, if the recursive formula is a sub n minus 1 plus some constant, then that would be an arithmetic sequence. And then if it's times by some constant, that would be a geometric series. So this is some sort of mix of a geometric and an arithmetic, because I'm both timesing it and adding -10. So it's got elements of a geometric series and an arithmetic series, sequence, I should say. So you could write it explicitly. And if you want to, awesome. If you're curious what that answer is, let me know in the comments down below. I can make a follow-up video on this, but I'm actually not going to do it for the sake of this video because one, it would take a lot of space. I'd have to zoom way out and show you all the steps for it. And I think it would just take a lot of time as well. And I don't want to make the video too long. So what I'm going to do actually is I'm going to pull up Desmos and I'm going to rewrite it so that it's in terms of x and f of x. And I'll show you what I'm doing in a second here. Let me go ahead and finish writing it out before I switch it over. So I'm going to write it the way you know what? No, I'll put the x on the back end just so that it's exactly like how it's written, how the book wanted to write it, I should say. So times x minus 10. Okay. So I'm going to show you what I've got here on Desmos. You can do this on a graphing calculator or even on a scientific. It would be a little harder on a scientific, but you could do it. And they want to know after 1 year, right? So they want to know what's happening after 12 months. So I'm going to pull this over here so you guys can see this too. I don't need it to go that far over. Let's put it right here. Okay. So here's my f of x. Now I'm writing out this function, but remember this function is actually just a straight line. Right, so I'm not going to use it in a traditional sense. I'm not just going to follow out the line because then I would be treating this recursive formula as if it were an explicit formula, and it is not. I want to know what f of 1000 is, right? And the reason why is because that would be the initial amount, right? So when x is 0, sorry, when x is 1000, so this would be when I'm plugging in a 1 into the actual recursive formula, I would be finding out a sub 1 equal to a sub 0 times 1 plus 0.05 over 12 minus 10. Or if you wanted to put the a sub n minus 1 on the back end, that's fine too. So I would be timesing 1000 by 1 plus 0.05 over 12, whatever that is, and then minusing 10 from that. And that gives me this number. So this number looks like it's some sort of fraction because I got that 0.6 repeating thing on the back end as a 7 because it's rounding up to 7. But that's definitely a fraction there. I could actually do this and get an exact answer. And that way I can go ahead and type that in back into the problem. Now, so this answer right here is when n is 1. I want to know when n is 12. So we're going to count here. This is 1. So I'm going to copy and paste this over. This would be 2. So that's the 2. This is the 3, and I'm no longer able to write it as a fraction. This is 3. This one would be 4. Notice it's slowly going down. So that one's 4. 5. 6. 7. Almost there. 8. Any good jokes? 9. 10. 11. Almost there. 12. Ah, okay. So this is the amount that's in the account after 12 months. $928.37. So we're going to write that down. 928.37. So 900, I already forgot. My working memory is terrible today. 928.37. 928.37. Okay. So that looks like that's the amount after 1 year, so after 12 months. Is the amount increasing or decreasing? That's definitely going down because we started off with $1,000. Suppose that instead of $10, a fixed amount, D dollars, is withdrawn each month. Find a value of D such that the amount in the account after each month remains $1,000. So this actually is maybe not as hard as you think it is, because in order to figure this out, all we really have to do, let's get rid of all that for a second. All we need to do really is go here, get rid of this 10, and we just need to figure out what would happen if I plug in 1,000. The reason why this is helpful is because what is this number after 1 month before I take away the $10, right? Because we're trying to figure out like how much money can I actually pull out. Well, it looks like approximately I could pull out $4.17. Do you see that? Because if I subtract, if I go here and I minus $4.17, now I'm very, very close to 1,000. Now it would technically be just under 1,000. This would round to 1,000 if you're rounding to 2 decimal places. So if you're going to keep rounding to 2 decimal places every time, then this would actually be fine. If you wanted to be really, really nitpicky, maybe you could go down to 16, and that way it would be, just over 1,000. So you'd have at least 1,000 in the account. There isn't a perfect number here because if you go with $4.16, you're going to have a slight increase, and if you go with $4.17, you're going to have a slight decrease. So there is no perfect amount because, cents only stop at the second decimal place, right? So there won't be a perfect amount, but I'm going to move this back over here real quick, over my monitor. Let's look at the question and see if we can be a little bit nitpicky here. Is the amount increasing or decreasing? C, it's decreasing, right? Suppose the instead of 10, fixed amount D dollars withdrawn, find the dollar D such that the amount in the account after each month remains $1,000. So they're making it sound like just exactly 1,000. I guess you could make a point to say it would be $4.16 or $4.17, depending on how you look at it. Like I said earlier, if we did $4.16, or was it 15? No, it was 17. $4.17. And then you kept rounding after each iteration, then you would have exactly 1,000, and then it would stay like that. So with that logic, $4.17 would make sense. $4.16 if you're not going to round after every iteration. However, if you're not rounding after every iteration, you would technically go up over time, a little bit at first, and then it would start to take off more and more and more over time. So you could go with either of those options, really. I think I looked up the answer just to see if I'm making sure I'm not making any mistakes on this, and it's a little harder to find the answer because it's an even. But hey, that's what check is for. So let's B, calculate after 1 year. Wait, they're actually saying, oh, that's weird. A12 is equal to A11. 1 plus 0.05 over 12 minus 10. We can solve the equation for a12 to get a12 is equal to. Oh no, this is incorrect. This is an incorrect. So this is the downside of Chegg is that sometimes you get like these, I don't know, these like these AI answers or something, and AI does not know how to solve word problems. It's weird because they can do crazy good calculations like a calculator, but then they'll make random math errors, and it's so weird. And I don't know enough about AI to know why it's doing that, but it does. It makes these random errors. So it's trying to plug in 1,000 for a sub 11, and you wouldn't be able to do that. So that answer is incorrect. Let me see if the other one, what they put, just to be curious here. Now we're looking for answer for D. If D is greater than the amount calculated in part C, what did they get for C? Fixed amount each dollars. Well, part C is just asking if it's increasing or decreasing. Can we calculate this following equation? Minus a sub n. If D is greater than the amount calculated, then the amount, then eventually the account will be empty. Okay, that's not, hold on, that's not answering the question. Oh, you know what? This is a different version. Hold on. This is a slightly different version of the question. Let me see. I have it, several of these pulled up to make sure that I got the correct version here. What happens if D is greater than? This is the same version. Hold on. Okay, what's this version? Yeah, here we go. This is the correct version. C is the amount increasing or decreasing. Suppose that instead of 10, fixed amount D, dollars would only find the value of D, so remains 1,000. Okay, this is the correct version here. And this is actually done by a real person. You can tell because they just posted their scratch notes here. So hopefully they didn't mess up. That's answered by a calculus expert, apparently. Okay, so let's see. That's part A. Sorry, this is taking a second, guys. I'm pulling it up for you over here. All right, so part B. Yeah, part B takes a while to do. Okay, so they ended up getting, what did we get? Oh, we got the same thing as they got. Nice. 928.37. Yep. Awesome. Okay, cool. That makes me feel good. So we're on the right track here. It's decreasing. Part D. Suppose that the amount is just D. Now he said $4.17. Okay, I was kind of leaning more towards that because if you round to the nearest cent each iteration, that kind of makes the most sense to me. So yeah, $4.17. I think I would agree with that. So then part E, what happens if D is greater than this amount? If D is greater than this amount, you're pulling out more than the minimum to like keep it level. Then it would keep decreasing and decreasing and decreasing until you ran out of money. So if D is less than, sorry, more than, if D is more than $4.17, then your account will run dry eventually. And if D is less than that amount, then your account will increase, and actually it'll increase exponentially over time. It'll really take off. So there you have it. Hopefully that was helpful, and that ends the next part 2 of this series on series. This has been quite the undertaking. I didn't realize there were so many questions, and I'm doing this series. So we're done answering the question. I'm just kind of giving you the idea of the series behind all this. So if you're done, you can go ahead and click off. Go check out the 5 math mistakes everyone makes and how to avoid them. By the way, it's a free PDF guide I created. The link is in the description down below, myersmathematics.com. So go check that out, free guide. But the whole idea here, if you're wondering, like the whole like why did I do it the way I did it? So one, I did this over here because this galaxy pin marker I was using to represent the number 30 because I didn't want to write series out the word series out 60 times. Now in the next time I pick this series on series back up, I probably will have like a number for 30, but also have a number for 10. because it's just a little ridiculous writing series out this many times. It takes a long time to do all this. And granted, I kind of do it to myself, right? Because nobody's forcing me to do this. But yeah, so I just got a little creative with it because this video is going to come out on June 30th, the last day of a month that has 30 days. I'm doing the series on series only in months that have 30 days because it's easier to keep track of the math, which is ironic because I'm a math teacher. But hey, I'm giving myself some breaks from now and again. So so that's what's happening here. So that series that's in the galaxy pin, or rather the lack of galaxy pin in this case, represents the number 30. And then I wrote out the word series 30 more times in red and in white in order to represent 30 more, 30 and 30 making 60, because this is number 60. And that's the theme that I have going on for these, is that I'm going to have the word series written out that many times, unless I have the word series written in Galaxy Pen, and then I have it, representing the number 30. So that's just representing the series that came before. And I'm probably going to keep that theme throughout this series on series. So that's what that is. And then, of course, American flag, because July 4th is only a few days after June 30th. July 4th is the American Independence Day. So an American flag to represent American Independence Day. I was like kind of leading up to this, by the way, because if you've seen the last couple videos, um, they all kind of start to look like flags a little bit, different kinds of American flags. And that's kind of what I was going for. And I was kind of building up to this. And then I was like, you know what? I'm going to go all out for the last one. Who cares if it takes all night and I don't end up going out and getting as much of an exercise done as I thought I would. It's fine. Dieting is for quitters. Um, but so that's why everything is the way it is. If I didn't answer your question about why all of this crazy stuff is here, you can let me know in the comments down below, I guess. Also, let me know in the comments down below if I have an answer that, or if I don't have an answer that your professor is adding, or maybe they're looking for something more precise. Because I kept things pretty simple as I could. I like to keep things that way because I think it makes more sense. But if the professor is looking for something a little bit more mathematically rigorous, just let me know as much as you can about what that looks like down in the comments below, and I'll work on making a follow-up video for you to help like more accurately answer this question. Now, granted, the answers I gave in this question are the answers. I know from my own math expertise, and also confirming it with another source to make sure that I'm on track here and I'm not feeding you false information. So it's been double checked here, checked by myself, checked by another math expert over here. So these answers are accurate and correct. But I just mean that sometimes professors will go beyond the book. They'll say, "Oh, well, I'm going to add some extra stuff to this," or "I want you to answer it in this way," or something like that. So if they're adding or changing stuff, just let me know what that looks like, and I can make a follow up video on that to help you out. But other than that, this has been the end of part 2 of this series on series, and I hope that you've been enjoying them, that they've been helping you in your Calc 2 class. And I'll catch you guys again when I pick this back up in, let's see, January, February, March, April, May, June, July, August, September. So in September has 30 days. Little knuckle trick you can use to remember the months and the days that are in the months. So back up in September. So I will see you then, and y'all have a good one. Blessings.